Hello everyone, my name is Amit Sharma. I head technology for Dream11, which is a fantasy sports platform startup based out of Mumbai. We do cricket, football, kabaddi, basketball, and our most recent sport, hockey. And so today I'm going to talk about how we use Amazon Aurora and Amazon ElastiCache in our tech stack to scale our platform to actually, as we've seen our rapid user growth, and how we've actually scaled our platform to serve the high rate request rate on our platform. So a little bit about me. I'm the CTO of Dream11. Prior to Dream11, I spent around 10 years working in the Valley. I spent around 5 years working for Yahoo, and then I moved on to Netflix. Some words that describe my background are large-scale distributed systems, big data on the platform side, open source technologies, and of course, working for a very long time at Netflix. Got a lot of exposure to the AWS ecosystem while I was there. I did my master's in computer science from the University of Massachusetts back in 2007. And that's when I moved to California to join Yahoo. For those of you who don't know what fantasy sports is basically what you do is you select a match from a live match from an upcoming live matches, and then you create a team of players and then compete in contests with other users that actually create their own teams. And as these players perform on the real field, you get points, and based on that, your team gets total points, and then you start competing with other players, right, based on this. We've had a phenomenal growth story, and this is our growth in the last 5 years. Back in 2015, we were only 1 million user base, and we are actually almost at 50 million user base today. And by the end of next year, we projected to hit 100 million user base. What this user base of 50 million means is there's a very high engagement on our platform. And this engagement is at its peak during the biggest sporting event in India, which is called the Indian Premier League, which is a cricket tournament that happens in April, May every year. And just to give you some context about what an IPL in India means, this is the viewership of, it's like the Superbowl of India, right? So the viewership of Super Bowl 2018 was around 114 million users. And the IPL final, which was played back in May in 2018, the total viewership of that was 174 million people watched the IPL final. Every year, in April and May, what happens is our traffic patterns actually increase by a magnitude. So back in 2016, when we first started gaining traction on the platform, we hit a peak traffic request rate of 1,200 requests per second, and we were very thrilled. But we dwarfed that the next year. We went 10x, and we started serving 12,000 requests per second. And we again had a 3 to 4x growth next year, and we went to 48,000 requests per second. So every year we deal with this challenge of how do we scale our platform, because as our user base keeps on increasing and people get more engaged with our product, we need to build a tech infrastructure that is able to handle these volumes. A few more numbers. So 90% of our user base is on Android. We have 12.5 million active users, 2.4 million or maybe a little more right now, daily active users on our platform. Our peak concurrency in IPL last year was around 750K on Android alone. And across all platforms, we were just under 1 million concurrent users. Another very interesting characteristic of a fantasy sports platform is that the traffic patterns are very spiky in nature. So because you're very closely tied to what happens in the real world, you'll see the traffic patterns on the servers are on an average of, say, maybe 2 to 3 million RPM. This is our leaderboard traffic. And then suddenly an interesting event happens in the game, and within a minute, our traffic goes from like 2 million to like 7 or 8 million RPM. So one of the side effects of this is we always have to provision our infrastructure for that peak traffic. Auto-scaling doesn't work for us. We cannot be a reactive system. By the time we realize that we need more servers to actually serve this traffic, the surge actually just passes, right? So we cannot do that. So we have to provision at peak. We're trying to solve this problem by some innovative solutions, maybe offload the peak traffic to using some Lambda or something, but we're still trying to figure it out. But for now, we just provision our servers of a peak capacity for every game. So this is the nature of our platform, and we back in 2016 we were a very lean team, and we wanted a very like a quick shortcut to scale is what I call it. So we introduced Amazon Aurora into our system, and why Amazon Aurora? So some of the things we use about Amazon. So if you see, we are heavy users of Amazon Aurora. We use various instance types. We have total around 60 to 70 different RDS clusters in our platform right now. Total instances between the read replicas and the master. And some of the features of Amazon Aurora that actually made us pick it, I'm going to talk about next. So read replica. So in a typical MySQL environment, what happens is as the load on the master increases, the replica lag to this read goes up, right? And it can go hover from anywhere from a few seconds to a few minutes. But with Amazon Aurora, the replica lag is consistently less than 20 milliseconds. Now, what does that mean? For us, what that means is we can actually provide a very strong consistency, consistent behavior to our users by actually redirecting all our write traffic to the master, and all the read traffic goes to the readers. So when a user on our platform joins a particular contest, he sends a request in, the request goes to the writer, he joins the contest, and immediately queries back all the details of the contest that he's just joined. Now, because of the low replica lag, we're able to actually provide this behavior by using the readers. And as of now, Aurora provides around 15, up to 15 read replicas. So as your read traffic increases, you can keep on adding read replicas, and you just get horizontal scalability out of the box without doing anything about it. And at that point, this was the most sensible thing for us to do to serve the traffic patterns that I actually talked about earlier. Another good feature about Aurora, the reader endpoint, all these read replicas are actually behind a single reader endpoint. So it's basically abstracts out all the details from your application. Your application just connects to the reader endpoint, and behind the scenes, the load balancing is done by Aurora itself. Fast failovers. So any DevOps engineer would know what a nightmare it is when you actually, your master of your MySQL instance actually goes down. For us, in Aurora, what happens is whenever a master actually has a lot of load or has an issue, what it does is it automatically fails over, and one of the read replicas is promoted as a master, and this entire thing happens very, very quick. So one of the ways we actually use this is if you want to do a runtime instance upgrade, if you're supposed to, for us, what happens is for different games, the load that we expect is very different. So if you have a match in which you want to use an R4 16x, and then suddenly, once the match is done, you want to go down to R4 8x. We don't want any downtime when we actually do these instance modifications. So what we do is we create a read replica of the size that we actually want, and then we trigger a failover so that the read replica becomes a master, and the master becomes a read replica, and then we get rid of the old master. So this way, we're able to actually do runtime instance upgrades because of the fast failover feature. And majority of the times, the failovers happen in like less than 60 seconds. It's very rarely that we've seen a failover taking more than that time. And because of the short duration of the failover, majority of the times your applications are not affected at all. So that's pretty cool. Just like anything else in the Amazon ecosystem, Amazon Aurora plays very well with the other components. So it has an optimized load to S3. So what happens is all the data that you're writing to the Amazon Aurora database, you can very efficiently dump that entire data in S3. Now, we use this in a few different ways. So we have a lot of batch processes, some analytical processes that actually consume the data that is written in our Aurora database. So we run those applications on top of S3, so we use it for that. Our leaderboard is actually a point calculation system that reads this data from S3, runs it on Spark, does all the scoring and ranking and calculations, and load this data into Cassandra, and then we serve the leaderboard from Cassandra. We also generate a PDF file for each and every contest that we host, just to create transparency in the system. So all the teams for all the users are locked right at the match deadline, after which you cannot change your team. So we do this as well, so we read that from S3 as well. And we are actually, by dumping all the data in our transactional databases onto S3, we've kind of created a data lake for all our transactional data, and then we run ETL processes on it, and then we load the data to Redshift. Another cool feature is the data migration service. What you can do is you have a source Aurora and you have a destination Aurora. You just hit the DMS service, and the data is just migrated. And in majority of the times, what we've seen in our experience is that this data migration, the lag is less than a few seconds. So we use this feature when we're actually carving out from our monolith to microservices. So the biggest challenge that you have when you're carving out microservices from your monolith is the tight coupling of the data. So what we did was we created a DMS service, we created new Aurora, and then we carved out the application logic of our authentication service, and we moved on to the new servers. All the read traffic to the authentication service was started serving through that destination Aurora, and all the writes were still happening to the were still going to the source Aurora. So this actually helped us a lot doing that. Moving on. So that was Aurora. So there are 4 primary use cases for which we use Amazon ElastiCache. It's the de facto standard for us when it comes to any kind of caching needs. So anytime we want to put any cache between our persistent layer and our servers, we actually use Amazon ElastiCache. Session management. So over the years, all our web sessions are actually stored in. So we don't use any database for our session data. What we do is we put all the session data in a Redis. So this is very important, right? Because if we at any point of time lose this information, what this results in is all our users would get logged out. And in the last 2-3 years, we have got one big Redis cluster in which we put all this data, and it has never given us any issues. It's just worked fine. So it's worked fantastic for us. We also use Amazon ElastiCache in 2 different use cases. I want to do a deep dive on this in the next couple of slides. One is contest queues, and one is an event sync system. When it comes to contest queues, just to give you I talked about how we host contests for users, right? So users create their own teams and they join contests. So these contests could range anywhere between, say, a 2-member contest is the smallest contest that we have, and the largest contest that we've hosted is like 1.5 million people in a single contest. So that's like the range of contests that we have. So just before a match deadline, we get a very high rate of these contest join requests. So for these smaller contests, what happens is, for a typical like 2-member contest, what used to happen is we used to get like hundreds of people trying to join that 2-member contest, and then all these requests used to get serialized, and every request used to lock the row in the database, join the contest, and then release the lock, and then the next request would come in. So the result of that, what used to happen is, of all the hundreds of requests that we actually got, the first 2 were able to join the contest, and for everyone else, we used to show them a message saying, contest full, please try again. And behind the scenes, every time a 2-member contest gets filled up, we regenerate that contest. So that was the model that we were employing earlier. So we wanted to do a better job at actually solving this problem, and then to give a better UX to our users as well. So we actually decided to take out locking completely from the system. So what we do now is we pre-generate a lot of different instances of these 2-member contests beforehand, and then we generate tokens for every entry into that system, and we actually put all those tokens into a Redis sorted set in ElastiCache. So for example, a contest of type C1, we would probably generate like 100 of those contests, 200 tokens in total, and put all those 200 tokens in the Redis sorted set. And instead of routing the requests directly to the database, we actually serialize it, and we send all the requests to Redis. Every request gets a token, goes to the database, and then it becomes an insert-only system for us. So on the front end, what we did was we changed the UX, we tweaked the UX a little bit, and when the user actually sends the request to join a contest, we actually explicitly say that if we cannot actually put you into this particular contest, is it okay that we put you in a contest of a similar kind? And if the user says yes, then we just let them go through the system and do it. So earlier, the entire thing used to be within the database, but now the source of truth gets divided. Like, so some information is in the database, some of it is in Redis. So we need a reconciliation system, right? So what we do is we wrote a recon cron that periodically runs and tries to see if there are any discrepancies between the actual contest joins that are happening in the system and any tokens that are actually out of sync between the Redis and the database. And if there is, this cron actually automatically fixes. So it's like a self-healing system that we've created that identifies these problems and then rectifies it on runtime. So there is no manual intervention required. I want to spend a few minutes talking about our leaderboard solution. So as I mentioned earlier, right? So what we do is, as soon as the contest, a match deadline hits, we actually move all our contest join information onto S3, and then we use Spark to read the data, and we load the data into Cassandra to serve our leaderboard. So, but we do this calculation once every minute. And for every snapshot that we create every minute, we have a unique event ID that is attached to that snapshot. So when the users are requesting, we want a very strongly consistent view for all our users that are actually looking at our leaderboard. So we don't want different users to see different versions of the leaderboard, so they all stick to a particular event ID. So every time we regenerate this leaderboard for a particular snapshot, we need a mechanism to actually tell all our servers that this is the latest event ID, for which they need to go to Cassandra and get the leaderboard data. So the way we've done this is all our application servers actually subscribe to an Amazon ElastiCache. So ElastiCache provides a publisher subscribe feature. So all these, what we do is every time we recalculate this leaderboard, we let Amazon ElastiCache know this is the new event ID. It publishes an event. This event actually goes to all the various servers, and then they realize that this new snapshot of the leaderboard is available, and every new request that comes into the system actually then starts going to Cassandra and then fetches the latest data. So we also have another layer of optimization because of the higher rates of traffic that we actually generate, right? A network I/O also becomes like a latency factor for us. So what we do is we have a local Redis instance running on each of these servers as well. So at the start of the minute, when a new leaderboard snapshot is generated, all these Redis instances on the nodes are actually empty. But as and when requests start hitting these servers, and the server gets data from Cassandra for the same event ID, it starts populating that local Redis, and that local Redis starts getting hot over a period of time as more and more requests get in. So during the latter part of the minute, we are able to serve majority of the requests right from the local cache itself, and we don't even need to go to the Cassandra or any kind of external cache to actually serve that data. So we put in a lot of work in actually re-architecting the system, moving to a completely distributed architecture over the last 2.5 years. I'm also going to do a chalk talk on this, where we're going to talk about our journey as to what were the challenges that we faced as we moved from a monolith to a microservices. But as of now, if you look at our technical stack or architecture, this is what it looks like. So we've carved out our so some of the services that we created from scratch, which were never part of the monolith, like the aggregation, loyalty, etc., were actually created standalone. And a lot of these services we've carved out over the last 2 years. Some things that are very, very difficult to carve out is the user service. We actually left to the last. Wallet service and promotions. We are actively working on this, and our goal is that by beginning of IPL 2019, we should be able to move to completely distributed architecture in the backend. And we choose the right technologies for the different use cases based on what is needed, but at the same time, we don't want to get spread too thin. But as of now, this is our technical stack that we're using. So we use a combination of Amazon managed services and open source components to power various parts of our infrastructure. And these are just the key components, right? I mean, of course, we use a lot of small stuff as well, but this is primarily the things that actually power our architecture, and so far has been working pretty well for us. So that's it. I'll take questions now.
Awesome. Well, let's give Amit a hand. So for questions on Startup Central, we've been using Slido. So if you have questions, go to Slido on your phone. Use the hashtag startup. You can enter your question. You can upvote other questions. And then we'll just kind of work our way down the list there. So for now, we'll start with the top one here. How do you scale when you write requests start peaking?
So right now, the only write request that we have is contest joins, and so far we haven't reached a place where we actually need So to scale that too much right now, so we haven't hit that issue as of now. Uh, but a place where we did hit, so as I was talking about our leaderboard, right? So the leaderboard data keeps getting bigger and bigger. So for the IPL final last year, we had total number of around 3 million contests total. So all of these contest leaderboard is regenerated every 1 minute and written. So we wanted a system that actually is a very high write throughput. So for use case like this, that's why we chose Cassandra, which is actually optimized for writes. And if you actually do the data models right on Cassandra, then your reads just becomes like a pointed query, and the writes are like very, very fast. So we moved our write-heavy intensive workload to Cassandra to actually scale.
Cool. I guess I can answer that last question. The video will be posted online. It should take about 24 to 48 hours, but then they'll be live, so you can rewatch anything you might have missed. Here, we can jump into this one. What's the max throughput of Redis, and how many instances do you need to support the load?
So I think we've actually, in our use case, we've seen somewhere in a few million RPM throughput. And our instance, I think our instance size, the largest instance we were running was, we had a Redis cluster with 5 masters and 5 replicas each. So 30 node cluster is what we were using at that point of time. And the instance size was, I think if I correct, R3 8x large.
Any other questions?
Sure. So the fact that you're using Redis for some critical information, how do you deal with that if that cache dies or something
Say
like
that
that?
again?
So you're using the Redis cache for session information and things like that. Are you worried of losing that or anything like that?
Yeah, I'm always worried of losing that, but it hasn't happened so far. So it's a very, very reliable system, right? It's like it very rarely goes down. It has, I mean, we've faced very rarely have we faced any issues. So some of the issues that we face with Redis is network throttling, or hotkeys is one of the biggest problems that we've actually faced, because you cannot have more than 5 read replicas at one point of time. So the moment your read throughput reaches a point where you max out the resources on your 5 read replicas, you have no choice but to spin up another Redis cluster and then replicate that entire data to the new cluster. That's the only problem that we've actually hit. But reliability-wise, we've not had any issue. So for us, majority of our workloads are not very high memory intensive. So the data that we have is very small footprint of memory, but the request rate is very high, so we need to, the throughput is on the readers because of that. Memory is not a problem for us.
2 questions. I didn't see how you expose your microservices. Are you using an API gateway like Zool or Kong? And then my second question is, when it comes to fantasy, you're doing a lot of point calculations. Is the point calculations, because they're specific to leagues or specific to players, is it real time? Where did you offload that? Did you use lambdas? How did you solve that problem?
The point calculation?
Yeah.
So for the first question, we actually built our own edge layer. So the first thing that we did was, when we actually started carving out our microservices, was we realized like we needed a lot more fine-grained control based to how those requests are routed, because we had to get the data from different services, massage them. And also when we launched a new service, we started offloading a part of, so some of the smaller games on our system, we actually started offloading to the new services that we were creating. So we created our own edge layer. It's called the coordinator. It's a very simple stateless system. All it does is it has the ability to actually route to various endpoints and actually get the data back. So we did try using API gateway, but majority of our traffic originates from India. So the way the traffic was routed for that, it was actually not able to, when we did our load tests on API gateway, it was not able to scale to what we needed, right? For point calculation, I don't know, so we have a Spark plus Cassandra based solution right now. So what we do is, as I said earlier, so what we do is we read the data from S3 every minute, and we calculate the points and ranks of all the teams for all the players, and then we load that data into Cassandra, and then we serve the data out of Cassandra.
All right, well, it looks like we have a Slido question asking, what are your scaling bottlenecks and kind of challenges faced?
So one of them I just mentioned, right? Hotkeys in Redis, right? So we have a service called a tour service, which has the metadata of all the games and the tours and matches and players. That it's like a very small data set, but it's pretty much needed for each and every request that actually hits our system. So when we carved out the system, we chose Redis as our data persistence store for that. And very soon, what we ended up having doing was to serve our peak traffic in IPL. We had 4 different clusters of Redis actually having the exact same data and using DNS to actually distribute 25% of the traffic to all of these so that the services have single endpoint to talk to. So hotkeys has been one of our challenges. Other than that, I think it's about you have the only way to serve large traffic and scale is to move to a distributed system. And to do that, when your data model is so tightly coupled, it becomes very, very difficult. So you have to very slowly carve out one piece at a time, trying to balance it out between if you become too aggressive and then carve out a very major piece, it can. So that's what we did. We picked the most complicated part of our system right at the beginning. It was called the contest microservices, what we carved. But it actually took us like 6 months to carve out just one single service. But once we got that right, we were able to carve out the next of the services easily. So trying to understand the data model and figuring out which pieces you can carve out, that's the only way to serve the traffic is to actually have microservices and distributed backend completely.
Cool. I guess last question on Slido. Do you interact with any third-party services, such as billing or a payment partner? And if you do, how do you handle outages and failures?
So yeah, so we work with a lot of payment gateways back in India, so a lot of it is manual right now. But recently we've introduced certain systems where what we do is we track the rate of failure. So we have multiple payment gateways, and in a priority order, right? And what we do is we collect statistics as to which payment gateways, what's the success and failure rates for these payment gateways, and the moment the rates, it's not the moment the rate hits a certain threshold, we automatically disable certain payment gateways and then enable the other ones and make them higher in priorities. It's tricky though, right? Because what happens is, anyways, during the day, the rate at which the payment gateways are serving requests or the payments that are happening are different during the day and night. So the system that actually recognizes that it's actually an indeed problem and not a false positive, there needs to be some intelligence built into that. And so we're still working on it, but this is the first step that we've actually taken.
All right, well, I guess that looks like it's all the questions. Let's give Amit one more hand for great talk.